Ed. It's a great honor to be here, and thank you for the invitation. And I really look forward to my science discussions later today. So this is work that I'm going to present on tropical cyclones, and there are actually quite a few contributors to this work that you could also see here. So this is Mu-Ting Qian. She is a student of Daeun Kim's, actually, from the University of Washington. And so she and I have been collaborating on a project related to tropical cyclones and the ability of artificial intelligence to predict tropical cyclones. This is Yuchen Tsai. She is one of my graduate students at Colorado State University, and she's using more traditional weather forecasting models to look at tropical cyclones. So I'll show some of that work. And then Daeun is a collaborator, and also Susanna Camargo at Columbia University, and Elizabeth Barnes at Colorado State University, who I think visited Seoul in October or November. She was here recently as well. So let me motivate what we're going to look at here. So we're interested in tropical cyclones. In their full form, they're called typhoons here in the Northwest Pacific. They're called hurricanes in the Eastern Pacific Ocean and Atlantic, but basically the same phenomenon. And obviously, tropical cyclones cause substantial amounts of damage, death, and societal impacts around the globe. This is one example of two tropical cyclones that occurred in 2020 that impacted Korea. So Typhoon Maisak and Haishen that both made landfall in Korea and caused quite a bit of flooding and damage. One thing that tropical cyclones tend to do, whoops, wrong direction. Tropical cyclones tend to do that we're going to take advantage of for the purposes of this talk and talking about prediction of tropical cyclones is that they tend to cluster in time. So they, multiple tropical cyclones often can be seen during any one time and during any 1 or 2 week period. This is one example for the eastern coast of the United States. This is at nighttime, so you can see Florida here and the lights in Florida. This is Miami. And during this time in 2017, you could see that there were 3 very strong hurricanes that existed during this time. So the environmental conditions, the conditions of the atmosphere were extremely favorable during this time for multiple storms. You could even also see this in the Northwestern Pacific. So, for example, this is November of 2024, so just several months ago, where there were actually 4, typhoons and other forms of tropical cyclones occurring in the Northwest Pacific at this time. So Korea is up here on the upper part of this this map. So there are, again, periods that are very, very favorable for tropical cyclones, and also periods where you see nothing going on. So we're going to look at, whether we can exploit these periods of suppression and enhancement to, think about tropical cyclone prediction, several weeks in advance. One of the phenomena that Heme studies quite a bit, and I study quite a bit, that helps to lead to this modulation of tropical cyclones is something called the Madden-Julian oscillation. And this is a composite, or sort of a typical life cycle of the Madden-Julian oscillation that was created by Adrian Matthews at the University of East Anglia in the United Kingdom. And you can see time ticking here, so this whole animation takes 40 to 50 days to complete. What you can see here is that it starts with precipitation in the Indian Ocean that then moves slowly off towards the east with time, and then eventually dies out near the dateline or slightly off towards the east. And this whole cycle takes 40 to 50 days to repeat. this is what things look like mainly in our wintertime. In the summer, it looks a little bit different. I'll show you what the summer looks like on the next slide. But as I'll point out later, this phenomenon, as it moves eastward, can cause conditions to be favorable for tropical cyclones to occur as it progresses east. So very nice animation that many people show to motivate what the Madden-Julian oscillation looks like. So the Madden-Julian oscillation affects wintertime weather over places like Korea and North America. It affects droughts in various parts of the tropics, like Indonesia and the Amazon. Affects a lot of different extreme weather phenomena. But what we're interested here is its effect on tropical cyclones. I'll show its effect on tropical cyclones, but one thing I wanted to point out before then is this is what the cycle of the MJO looks like if you turn it into a series of slides. And so much like before, you could see it blowing up here over the Indian Ocean and then moving off towards the east with time. And so each of these panels is like 10 days apart, so it takes like 20 days for it to get from here to here. So that's the precipitation. The other thing I wanted to point out here, and this is very important for tropical cyclones, is you'll notice that there are winds associated with this Madden-Julian oscillation phenomenon. So these wind anomalies, in this case, these are anomalous winds blowing from east to west, can extend all the way out to the coast of North and South America. So not only does the Madden-Julian oscillation affect things over here in the Northwest Pacific, but there's also connections out here to the coast of the Americas. And so there's actually, as I'll show you later, tropical cyclone effects all the way across the tropics associated with this phenomenon. Of many climate models to simulate the Madden-Julian oscillation. And this also extends to other types of models as well, including weather forecasting models. And so what we're going to do here in the first part of the talk is talk about the ability of one specific weather forecasting model, the NOAA, National Oceanic and Atmospheric Administration model in the United States, to predict conditions associated with tropical cyclones. And then what we're going to do is we're going to use a newer type of model, which is a climate model based on artificial intelligence, a so-called AI climate emulator that was developed at the Allen Institute in Seattle by Chris Bretherton and collaborators. And we're going to look at the ability of this model to simulate the Madden-Julian oscillations modulation of tropical cyclones. So two different models we're going to look at here. All right, so first of all, let's look at, I'm not going to read through all these words, but let's look at this traditional model, weather forecasting model, put out by NOAA. And this is a study that Yu-Chen Tsai, one of my students, has led. And I only wanted to point out here that we're looking at forecast data from April of 2011 to March of 2018. So 7 years of forecast data where we initialize the model on the 1st and 15th of each month and then look at the model's ability to simulate tropical cyclone conditions out into the future. So there's a lot of equations on there. This is actually meant to scare you, so I'm not going to go through this in too much detail. But this is what a conventional forecasting model might look like. It's based on physical principles, first principles, and so if you remember from any physics classes that you've taken, there's Newton's first law: force equals mass times acceleration. So that's embedded within these weather forecasting models. So we try to predict a wind based on this equation. We have a thermodynamic equation that tries to predict temperature. We have an equation that tries to predict moisture in the atmosphere, water vapor. We don't want to lose mass of the molecules in the atmosphere, so we have mass conservation. And then we have basically Newton's first law of motion in the vertical, so we have a vertical force balance. And this is what a traditional weather forecasting or climate model looks like. So it looks simple enough, but the problem with a model like this are these terms here on the right that I have circled, and what these terms are essentially representing things like clouds in the atmosphere, really complicated things like clouds that are hard to represent properly in the model, mainly because we don't understand cloud formation as well as things like that as well as we should. So we have to use a process called parameterization in models to try to determine how and why clouds form and the effect that they have on the forecasting model. So in a traditional weather forecasting model like this, we have to come up with ways of accounting for these different terms. In the AI-based model, artificial intelligence-based model, I'll show later, it doesn't even try to do this. It tries to simulate weather and climate in a different way. But this is the problem with a traditional model that we've been trying to solve for 50 to 60 years. So you do clever things in your model, like there's in one of the versions of the NOAA model that we use here, it uses something called game of life rules to try to get clouds to clump together in the model to represent organized clouds. So you have to come up with clever ways to try to represent cloud systems in a type of model like this. And this is some work that Lisa Bankston at NOAA in Boulder in Colorado implemented in the NOAA forecasting model. And this particular way of causing clouds to clump together and organize actually produced some very good results in producing a better MJO in Madden-Julian oscillation in the model that I'll show later. All right, so how well does this weather forecasting model, developed in NOAA, actually do at producing the MJO and its modulation of tropical cyclones? I'm going to show you right now what that looks like. So here's a plot from observations. We'll call it observations, where we start out the MJO in a particular state. So we start out the MJO at the initial forecast time, where there is enhanced precipitation occurring here in the West Pacific Ocean on the equator, and there's suppressed precipitation here in the Western Indian Ocean. So this is what the Madden-Julian oscillation looks like, and this is time into the forecast. The time is going up here, and you could see, as expected, Madden-Julian oscillation moves off towards the east with time, and eventually reaches the East Pacific here. So reaches the East Pacific. And then this region of suppressed precipitation reaches the East Pacific, and it causes precipitation to decay. The model is here. So how well does the model do this? And if you cross your eyes, it looks okay, but you'll notice that there are some issues with how the model simulates the future. So the model actually has this precipitation region moving far too slowly. By day 20, it hasn't moved that far. It's gone to like 180 degrees, similar for this suppressed precipitation region. And then maybe more importantly, we're going to concentrate here on its effect on the East Pacific. So between these two dashed lines, you see that it tends to lock in one sign of precipitation into the East Pacific. And that's going to produce some really bad things if you want to predict tropical cyclones 3 weeks in advance. It looks very, very different than what you see in observations. So what's the implication for tropical cyclones? So in the tropical cyclone community, we know that there are multiple things in the environment that can make conditions more favorable for tropical cyclones. One is if you have high ocean temperatures. Another thing is if you have a lot of rotation in the large scale environment, so that tends to produce tropical cyclones. Another thing is low amounts of vertical wind shear. So if you have the wind blowing really strong in near where jet aircraft are flying, but not blowing very strong near the surface, you could actually shear apart or rip apart tropical cyclones. So you want the wind difference between the lower and upper atmosphere to be very different. And then you generally want upward motion, upward moving motion in the environment. So people, for the purposes of looking at tropical cyclone conditions in models, have come up with these so-called tropical cyclone genesis potential indices that talk about how favorable the large-scale environment is for producing tropical cyclones. This is one particular version of this that was generated by Moon et al. 2018. That includes 3 factors here. I'll show another one later. But how well are these predicted in that model that I showed you before? So I showed you that this MJO, Mad-Julian Oscillation Disturbance, tends to move too slow and produces East Pacific problems in simulating precipitation. Do these get reflected in tropical cyclones? And I guess the answer is yes. So we looked at this tropical cyclone genesis potential index as a function of forecast lead time. So this is out like 3 weeks into the future. And each of these bars here shows either in observations, which is in blue, or several versions of this NOAA model, which are in these other colors, what their prediction is for tropical cyclone favorability multiple weeks into the future. And you could see that the observations start out favorable and then get less favorable as time goes on. Most of these model simulations don't do that. So most of these model simulations have tropical cyclone conditions that are simulated very, very poorly out into the future, and actually conditions that are far too favorable for tropical cyclones at 3-week lead times. There is one exception though. This model here, which is called Prototype 8, this is the model where we included this game of life clumping together of convection to better simulate clouds, to better simulate organization. And that particular model does a really good job. So you can make physical improvements to models to make them do a better job of simulating tropical cyclones, but it's actually very, very difficult and a problem that we've been working on for many, many years. So what I'm going to talk about next is a different type of model that's recently been developed called a climate emulator, and see whether or not that particular model produces a better representation of these connections between tropical cyclones and the Mad-Julian Oscillation. So let's move along to here. So I'm going to show you some work that Mu-Ting contributed. So again, Mu-Ting used to be one of Daeun Kim's students at the University of Washington and now is at Colorado State University. And what Mu-Ting is looking at is this so-called Allen Institute for Artificial Intelligence, AI2, climate emulator, which is a neural network-based atmospheric model which is trained on observations. And then once it's trained on observations, you could run it during another period and look at its representation of climate, look at its representation of weather, and things like that. So we're going to be looking at some results from this particular model. And This model is trained on observations during the years I show here, so 1940 to 1995, 2011 to 2019, 2021 to 2022. I don't know the motivation for using these particular years. I didn't, train the model myself, but they did at the Allen Institute. And you'll notice here that there's a gap from 2001 to 2010, which is not in the training period. We're going to be looking at results during that period to look at the model's ability to simulate the MJO and its modulation of tropical cyclones. What is used is this model at 1 degree horizontal resolution with 8 terrain following vertical layers. So you represent the vertical structure of the atmosphere in 8 layers in this particular model. And what's spit out by the model are winds, temperature, humidity, precipitation, so many of the variables that we're interested in. And we could also diagnose tropical cyclones in this model, as I'll talk about in a little bit. All right, so what we're going to do here is look at model runs that Muting did from 2001 to 2010. And we have 10 different ensemble members for this same period that are started with slightly different initial states. So we start the model with slightly different initial states of the atmosphere, and they're run forward. And so we have 10 times 10 ensemble members, so like 100 years of data to look at with this model. Greenhouse gases are prescribed. We tell it what the sea surface, ocean temperatures look like. So it's just an atmosphere model. And it predicts the variables that I talked about before. And we're interested here not only in the Madden-Julian oscillation, but also tropical cyclones. And so to get tropical cyclones out of this model, we have to use a tropical cyclone tracker. So we have to identify the tropical cyclones, hurricanes, and typhoons in the model. And we do that using this package called Tempest Extremes, which was developed by Paul Ulrich and Colin Zarzicki in 2017. And other details are contained in this paper by Jen et al. 2025, which I could forward to people if you're interested. All right, so the first thing that we want to look at with this AI-based model is, does this AI-based model simulate the conditions that are favorable for tropical cyclones in the tropics? I mentioned one version of one of these Genesis potential indices I showed before. I'm going to show another one here. This is a Genesis potential index, which is developed by Michael Tippett and collaborators at Columbia. And what it diagnoses is the favorability for tropical cyclone formation here. That's what TGCI is going to represent. Favorability for tropical cyclone formation here. And it's based on the amount of rotation you have in the environment. So the rotation tends to support tropical cyclones. A moist environment, if the environment is moist, you tend to support tropical cyclones. High ocean temperatures, low wind shears, and away from the equator. So get away from the equator, higher latitudes are favorable. This is what the observed favorability for tropical cyclones looks like in ERA 5. You see favorable conditions in the Northwest Pacific, so we get a lot of tropical cyclones here. Favorable conditions here in the East Pacific, and also south of the equator, particularly in their summertime. This is what favorability looks like in observations. This is what the favorability looks like in the AI model. So the AI model is going to be called ACE in many of these plots. And what you could see here is that there's many regions of the tropics which the AI model diagnoses as being favorable for tropical cyclones. In fact, the values are higher, more favorable for tropical cyclones than you see in observations. There's a lot more reds here. And we think this is because this AI model, this wind shear term the wind shear is really low, so it makes it really favorable for tropical cyclones. So that's why it's it's a bit higher in this model than the real world. I'll talk about some implications of that in a little bit. How much time do I have left? 10 minutes, okay, yeah, that's fine. All right, so I mentioned that we use a tropical cyclone tracker to diagnose tropical cyclones in the model and observations, and wanted to show you, first of all, the formation locations for tropical cyclones, both in the model on the top and in observations here on the bottom. So each of those blue dots is where a particular tropical cyclone first formed. And what you could see here is, at first glance, it looks like the model does a reasonable job of capturing the distribution of formation of tropical cyclones. So it seems to be doing a very good job. If you look at the annual tropical cyclone numbers, it produces about the right amount of 80 across the globe, and so that's reassuring. So this seems like a success, for the AI model. If you look a little bit closer here, you'll notice there are some problems or biases in where tropical cyclones first form. So for example, you'll see here in the East Pacific, tropical cyclones in the AI model tend to form farther from the coast than they do in observations. That's something interesting. You see fewer tropical cyclones forming here in the South China Sea than you do in observations, maybe less in the Indian Ocean. So they're, generally it's a good job, but you'll notice some regions where there are some problems. We think that this region here, the model is having a difficult time producing the precursor or the initial disturbances that then form into tropical cyclones near coastlines. So we think that's a problem. I'll talk about that again later, but generally it's pretty good. Watt-Meyer here looked at tropical cyclone tracks, and if you look at the tracks of tropical cyclones after they form, it also does a reasonably good job. This is what observed tracks look like. Another representation of observed tracks, and this is the ACE model right here. So you see that there's a reasonable distribution of number of tropical cyclones, where they travel, and also, number of impacts in places like Korea. So the AI model does a reasonably good job. Okay, so I find this plot absolutely remarkable. So this plot here, all right, so let's go back here and show you what this looks like. Whoops, going the wrong way. All right, I don't want to give away my results. So you notice there's different regions here. So this is the East Pacific, Northwest Pacific, Indian Ocean, and then 3 other regions. So what I'm going to look at in the next plot is tropical cyclone formation in each of these regions and how it varies as a function of time of year. And this is what it looks like. So let's look at the Northwest Pacific, tropical cyclones that affect this region. Each of these is a month, sort of January, February, March, April, so on, all the way to December. And the black line here shows tropical cyclone number in this observational product. And the blue line shows tropical cyclone number as a function of month for the AI model. And most regions here, you get a remarkable correspondence to getting the right seasonal cycle of tropical cyclone activity, such that most of the tropical cyclones form in summer in this region versus winter. So I find this one of the remarkable findings from this model. There are some problems in some regions. The North Indian Ocean, in observations, tends to have 2 peaks in tropical cyclone activity, and this model tends to underproduce and not produce this, especially this first peak well. We think again that this model doesn't do the best job of always simulating the precursor disturbances to tropical cyclones, so that's one idea. I was talking about this with some of the people at Seoul National University, and they agreed with that hypothesis too. But most regions here, remarkable job. All right, here's another remarkable plot that I found from this particular model. So I talked about before the ability of many models to produce an Madden-Julian oscillation is very poor. This is the results from the AI model on the right. So what this is time is going up, longitude is going east here, and in observations the MJO moves east. This is a lag correlation plot for those who are in the know, but this is what the MJO looks like in observations. It's almost indistinguishable in this AI model. Absolutely remarkable how well the MJO is produced in this particular model, which is something that I've rarely seen for some of the more physics-based models that I introduced before. All right, so starting to wrap up here. Probably only have a few more minutes. Does this translate to modulation of tropical cyclones by the Madden-Julian oscillation as well? It produces a good MJO, but is the tropical cyclone modulation produced realistically? And the answer is yes. This is a snapshot of multiple phases of the Madden-Julian oscillation from observations here. And the colors represent, you could think about the colors as being precipitation, but this is also technically this genesis potential index that I talked about before. You could think about it as being precipitation if you want. So you can see the MJO marching forward, marching eastward with time as you go down in this plot. Also shown on here are tropical cyclone genesis locations. And you see in observations, you tend to get most of the tropical cyclones forming where you have favorable conditions associated with the MJO. This is the AI model, very, very similar as far as eastward propagation of tropical cyclogenesis conditions and favorable conditions tending to produce an increase in tropical cyclone activity. So again, very, very promising. And then if we zoom into a particular region like the Northwest Pacific, and look at that as a function of time, you see that there's a very nice correspondence between how the observations show the MJO's modulation of tropical cyclones to be and what you see in the AI model. Maybe I'll leave it at that right now and wrap up with some conclusions here. A little bit more discussion. All right, so ACE model, the AI model, does a lot of great things. It's not perfect. It doesn't produce enough tropical cyclones near land, so that's a problem, particularly if you're interested in coastal landfalling of tropical cyclones in Mexico. Then your AI model might not be that good for that. So that's something they need to improve upon. We think it's because tropical cyclone precursor disturbances, the big circulations that form the seeds for tropical cyclones, those are not as well simulated by the AI model. And there's things called easterly waves or monsoon depressions, things like that, that form tropical cyclones in various regions. The AI model doesn't do quite as well there. So that could be why things are deficient near land, because a lot of those disturbances form near land. So other dirty laundry I didn't talk about, interannual tropical cyclone variability is not as well simulated by ACE. So if you're looking at El Nino and put in El Nino background state, ACE doesn't seem to do as well with that for some reason. I don't understand that. And there also seems to be a larger larger variation of environmental condition, favorable conditions forced by ACE versus the actual number of tropical cyclones that are produced. So there's a mismatch there between how big the environmental changes are versus tropical cyclones. And we think that might be because the precursor disturbances are not simulated right. All right, so just to conclude, a few key points. We showed one traditional forecasting model that shows definite biases in producing sub-seasonal predictions of tropical cyclones by the Madden-Julian oscillation. But you can make physical parameterization changes to those models that help to improve prediction. So that's one way to go, I think, if you're thinking about subseasonal prediction of tropical cyclones, is to use a conventional model like that with physical improvements. But then I also showed you that there's been great advances made recently in AI-based models, particularly the Allen Institute emulator that I showed you, that produces a realistic MJO and realistic depiction of its modulation of tropical cyclone genesis. And models like this could be an incredibly useful tool for doing subseasonal prediction of tropical cyclone activity in various basins. Of course, the model has some caveats as well that I just talked about. Then last slide, we are thinking about some future work here. One thing that we are thinking about is what are the implications of future global warming, ocean warming patterns for tropical cyclone activity. So Mu Ting and Libby and I are thinking about imposing various assumptions about future sea surface temperature warming patterns and how those affect tropical cyclone activity. We're also talking about doing some paleoclimate, paleotempestology work, looking at last glacial maximum periods, Eocene warm periods, things like that, and looking at implications for tropical cyclogenesis. We're looking at other tropical disturbances other than the MJO, and we're also hoping to help NOAA contribute to model development and diagnosing their model to produce improved versions of the unified forecast system that I talked about before. With that, I'll say thank you and take any questions. Thanks.